Okay, let's start. So, can you hear me well? I am, yes, thank you. Okay, so I am Massimiliano Rossi and I will be the lecturer for you today. And so we are going to talk about the fast Fourier transform. And those, what I will tell you is based on lecture notes by Eric Demey, which was a Tata student, by the way. And yes, if you have questions, feel free to interrupt me, and I will try to check the raise hands and the chat and the Q&A as often as I can. So, okay, so let's start. Okay, so generally the fast Fourier transform is a very important algorithm, especially in digital signal processing, and it's very used. It's very useful if you ever edited an image or some audio. You will probably use the fast Fourier transform. I don't know if you were aware of that or not, but today we are going to focus more on the fast Fourier transform in terms of divide and conquer and in terms of polynomial. So, okay, let's see. So we have a polynomial. Which is a of x. We have the constant term, the linear term, quadratic term, and the last term, which is n-1 term. So this is the degree of the polynomial. A is as n-1. Okay, so I guess you all know polynomials. Okay, now we can write a polynomial in another form, which is by using a summation for k goes to 0 to n-1 of akx to the k. And we can also use another notation, which is an array notation, in which we just store the coefficients. And you can see this as like some samples over time, okay? So you have a signal that goes on the over time, and then you sample it at regular intervals or non-regular intervals, whatever. And you can see those coefficients as the values of the signal at certain timestamps, okay? Okay, now we have a polynomial, and what are we going to do with this polynomial? So we can do some operations, okay? So the first operation that you can think of is the evaluation. So we have our polynomial ax, and we are given a value x0. Okay, and we want to evaluate the polynomial for the value x0. So how can we do that? So how can we do that? There is a simple way. So we just go on over the polynomial and evaluate all the terms. So we evaluate A0, and then we sum it with A1 plus times X0. So we multiply X with A1, and then we multiply X0. So this is X squared times A2. So if we go on, we have that for each element, we spend an increasing number of multiplications. So for AI, we spend I multiplication. Okay. So in general, we will take O of n squared time. Where now by n squared time, we are considering the number of operations that we have. But there is a better way to do that. So I will just erase this. Okay. Which basically we can look at the polynomial and divide it in two parts. So the first part is the constant part. So we have A0. Okay. And we sum. We have the right part. So if you look at it, is A1x plus A2x squared plus going on. All the terms as an x. So we can collect the x at the beginning and write it like this. So now we have A1, which is the constant term of another polynomial. So we just divide all the right part of the old polynomial by x. Now we have A1 again, and we can do the same. Now we will have A2 times x, A3 times x squared, and so on. So we can just collect another x and put A2 plus another x, A3, and so on. The last one is n minus 1. And some close parentheses, okay? And to evaluate this form, this is called the Horner's form. Okay. Okay, and to evaluate this, it takes a linear number of operations. Because every time it's just one multiplication and one addition. One multiplication and one addition. Okay. After one, this is evaluation. Okay, let me write it. Evaluation. Okay. The second operation, it's the addition. So given two polynomial, we want to sum them. So given ax and the x, we want a polynomial cx, which is ax plus bx for all x's, okay? So how can we do that? So this is easy. So let me write down the two polynomials. E1x a2x squared, and so on. B1, B0, sorry, B1x, B2x squared, and so on. So what we want to do, we want to sum them. So basically what we want, so here we have, sorry, A0 plus B0, it's the constant term. And then the linear term will be A1 plus B1. And then the quadratic term will be A2 plus B2, and so on, okay? So we can say that CK is equal to AK plus BK for all K. So in this case, also the addition will take linear time, right? Okay, so the third operation we want to talk about is the multiplication. So given two polynomials, again, AX and BX, we want a polynomial CX, which is AX times BX for all X's. So if we take again our polynomials, 0 plus A1 X plus A2 X squared, B0, B1X, B2 X squared, and so on. Now what we want to do, we want to multiply them. So we do the classical multiplication. So now what we will see is that, okay, so the multiplication of A0 and B0 will be the new constant term. So you have A0, B0. Now the linear term will be, so I will multiply each element of A times each element of B. So the element in the multiplication that will be with the nx, okay, will be those two, A0, B1 and A1, B0. So you will have A0, B1 plus A1, B0 times x. And now for the quadratic term, we will have those three. So A0, B2, A0, B2, A1, B1, A2, B0. And so on. So in general, what we can say is that CK is equal to the sum for j's that goes from 0 to k of what? AJ times B k minus j. So you can see if k is equal to 1, then we will have A0 B1 plus A1 B0. Okay. And so to compute this, it will take quadratic time. Okay. So now what we want, we would like to reduce this time from n squared to n log n. And we will use the fast Fourier transform to do that. But the problem is, so now what we want, so we want to try to reduce this time. But to do that, the first thing that you can map is there another representation of a polynomial which let me do the multiplication in a faster way, okay? And so if you think about polynomial representations, so we have seen the representation A, which is the coefficient vector representation. So you have AX, which is A0, A1X, A2X squared, AN minus 1, X to the N minus 1. There is another representation, there are more. There's another representation in which we are interested today, which is called either point value representation or samples. So the samples, so what we have is we have a bunch of samples. Particularly, we have n samples if the degree of the polynomial is n minus 1. So we have samples like this: x0, y0, x1, y1, x2, y2, x n minus 1, y n minus 1. Okay, such that, so where we have that AXK is equal to YK for all K. So this is one point. The second point is that all XKs must be distinct. Why we need that? Because these, so if we have endpoints, okay, and all x's are distinct, such that A of xk is equal to yk, we have that this uniquely determine a polynomial of degree n minus 1. Okay, and this is given by that there is a theorem. So there are a couple of theorems. So this is given by Lagrange, and the fundamental theorem of algebra, which basically says that a polynomial of degree n has n root counted with multiplicity. So now we have this new way of looking at polynomials, which is by samples. So we take n distinct point in the x-axis, and we evaluate the function a in those points. Okay. So now we said that we were interested in those three operations: evaluation, addition, and multiplication. So how much does they cost in this new representation of the polynomial? So if you look, so we will start with the addition and multiplication because they are the simplest. So we have two train of samples, okay? x0, y0, x1, y1, x2, y2. So this is the samples of A. Those are the samples of B. Those are evaluated in the same, for the same values of X. I will say y0 prime. X2, y2 prime. Now, if I want to add them and to get C such that the new function C is the sum of the function A and B. So what I get is simple. I just sum the values of A and B in the corresponding position in X. So y0 plus y0 prime, x1, y1 plus y1 prime, and so on. Okay, so this is easy. So we have that ck is equal to xk, yk plus yk prime. And this takes linear time. It's a linear number of operations. Okay, now, second operation, I wrote third because was the third before. Okay. So again, we have those two. Okay, I'll write them back. Polynomial. And B, as before. Okay, and now we want to multiply them. Okay, I can see a couple of questions. Okay, the context of this and fast Fourier transformation. Yes, this is the fast Fourier transform. So the idea of the fast Fourier transform. So now what I will show you an algorithm which is called fast Fourier transform. Okay, which basically compute the discrete Fourier transform, which is the mathematical function. Okay, and we will see it in the context of polynomials. Okay, so we will use it to multiply two polynomials. Okay. No, the fact that they must be distinct is that otherwise you will evaluate the function the same point. So then there's another question about why the X elements must be distinct, because if they are not distinct, you are evaluating twice the same point of the function. And for the fundamental theorem of algebra plus the Lagrange interpolation, okay, we need that those points must be distinct. So you need n distinct points to represent a function which has a degree of n minus 1. Okay. So if you can think it like if you have a linear function, you need 2 points to identify a line on the plane. If you have a quadratic function, you need 3 points to identify the function correctly, uniquely identify the function in the plane. Okay. Okay, go back to the multiplication. So how can we multiply them? So we can basically multiply just the coefficient on the same sample. y0 times y0 prime. Okay, so So it's just, I want AX times BX. So if I evaluate AX and BX on point x0, then I want C, which is the multiplication of them. I just multiply the point in 0, okay? So X1 is Y1, Y1 prime, and so on. So here we have that CK is the XK times Y and YK prime, okay? And this is fast. Now, it's ON time. So while before the multiplication was quadratic time. Now, where is the problem? The problem is in the evaluation. Why? We want to evaluate the function, so we have AX and an X prime. I will call it X prime because X0 we use it for the points. Okay, X prime, and we want to compute A of X prime. Now, if X prime is in the set of X0, X1, Xn minus 1, then it's fine. This takes off and time. But otherwise, we need something that is called the interpolation. So we need to interpolate the points, okay? And and then once we interpolate the point, we get the polynomial, which interpolate the points, and we can evaluate in the X prime, which is not in the set of points that we have. So this requires interpolation, which takes O(n) square time. So just to sum up, so we have here is the coefficient representation. Here we have the samples. Here we have evaluation. Addition and multiplication. So we have ON time. Okay, I will avoid right time. So to perform the evaluation in the coefficient representation takes linear time for the addition, and quadratic time for the multiplication. Here we said the multiplication is linear time in the samples. The addition is linear time. The evaluation is quadratic time. So what the idea, so we would like to take the mean of the two columns. So we would like to have evaluation in linear time, addition in linear time, and multiplication in linear time. This is not possible. But what we can do, what we will do, we will show that we can go from one representation to the other representation in of n log n time using the fast Fourier transform algorithm. Okay, so the fast Fourier transform algorithm gives us a way to go from one representation to the other one. So what we will do is basically we will take the coefficient representation, we will transform it into samples, We will multiply the sample representation with the linear time, and then we will transform them back into the coefficient representation. So what we will get, and this takes n log n time because the highest term is n log n. Okay, so now, how do we sample? So if we have a function in the coefficient representation, how can we sample it? Okay, so we will see it in a matrix way. So basically what we have, so we have n samples, x0, x1, xn2, n minus 1. We'll write them in a matrix. So x0, x0 square, and so on, x0 to the n minus 1. And then the next row is x1, x1 square, x1 n minus 1, 1, next n minus 1, n minus 1 square, x n minus 1 to the n minus 1. So those x0, x1, xn are the points that in which we want to evaluate the function ax, okay? Now, what we will do, we will write here the coefficient of the function, a0, a1, and minus 1. So if you do this matrix times vector product, so what you will get exactly the evaluation of the function in the point x0, and we will write it into y0. Okay. So, and then you have the second row, find this column, you have a0, x1 times a1, okay? This will be y1, and so on. To compute this matrix, you can use the Horner's rule to compute each row. So to compute the matrix is quadratic time, but you can compute it once and for all. You can fix the axis and then you can compute it once and for all. So you can pre-compute it sometimes, and that's fine. So this matrix is called the Vandermonde matrix. And you basically have, I call it V. So you have that Vjk is equal to xj to the k, okay? For all jk. Okay, so with this matrix, we can go from the coefficients to the samples. We'll do the matrix vector product, which is B times A. A is the vector of the coefficients. Okay. So now the question is, how can we go back? So one way is you can see this as a system of equations, and you want to solve this for the values of x, okay? For x, okay. You can see this like a system of equation, yes, and you can solve it for the values of a's, so the coefficient, okay? So one method is to use Gaussian elimination. which takes cubic time. But so this matrix is pretty cool. So it has some, yeah. So the V is the Vandermonde matrix and A is the vector. So this is V and this is A, okay? Okay, so we can invert this matrix. So this matrix can be inverted. So what we can do is we can use again a matrix to vector with product. Which is P minus 1 times the values of Y gives us A. And this is quadratic time. Okay. But we can pre-compute this. We can pre-compute this. So now we haven't gone so far because we still have a quadratic time algorithm to do the transformation. So to go from coefficient to samples and from sample to a coefficients. But so what we have used so far is that the points, so the only constraints that we used is that the points must be distinct. But we didn't say anything about, we don't have any constraints about the values of the points. So which values will be used? Okay, so if we choose a special set of values, we can do better than O(n) square time. We will do it in n log n time. Okay. Now, yes, the Y is this vector here. It's the vector of Y. It's the vector of all the evaluation of the points. Okay. Now, so before I'll tell you how we will choose those special set of points of values of X, okay? I will show you how we will compute how we will perform the evaluation, okay, of AX. And we said we want to achieve it in n log n time. So this means that we will probably use some divider and conquer technique. So okay, so our goal is to evaluate A of X for all X in the set capital X, okay? And capital X is a set of n points, okay? If the degree of the polynomial is n minus 1, okay? So we have our polynomial A. So the first step is the divide step. Okay. So we want to take the polynomial A and divide it into two parts, such that the size of those two parts, they are of the same size. So half of the size of the original polynomial. okay? So there are two ways in which we can divide the polynomial. So basically what we want to do, we want to divide the coefficients, okay? So we want to divide the coefficients. There is two ways. Either we take the first n/2 coefficients and the second n/2 coefficients, but this is not a clever way to separate the coefficients now for this option, for this approach. What we will do, we will separate them between even and odd indexes, okay? We divide AX into even and odd coefficient. So we will have one new polynomial, which is A even of X, which you can write in the sum notation 0 to 2 minus 1. This is the floor. This is, to be precise, should be correct, I guess. So it's kind of n/2 elements, depends on the parity of n. And so we want to take the even one. So we take 2k x to the k. Note that now we will have the index, which is different from the exponent. The easiest way is to write them in the vector notation. So we have A0, A2, A4, and so on. And now we will have A odd. We can write the same. Now we have to take the seeding of F2k plus 1, because we need to take the odd one, and x to the k, which will be A1, A3, A5. And those are new polynomials of degree n/2, almost. Okay, depends on the parity of n. n/2, n/2 minus 1. Okay. Okay, no, they are of degree n/2 minus 1 or n/2 minus 2. Should be, yes. Okay. Now, the second step is the conquer step. But we will leave it for later, because to do the conquer, we need to know how to combine them, which is the third step of the divide and conquer. So how do we combine them? So we have AX. So what we want to find that AX is equal to A even something plus A odd of something. So we can do it step by step. Okay. So we have AX. What is AX? A0 plus A1x plus A2x squared plus A3 x cubed plus A4 x fourth, and so on. Now, A even. What is A even? Is A0 plus A2x plus A4x squared plus A6x cubed, and so on. And A odd, what is A odd? Is A1 plus A3x plus A5x squared plus A7x cubed, and so on. Now, we want to combine them. So we want to combine A even and A odd, and we want to obtain again AX. So if you look, you have that A0 is A0 in A even and A0 in A odd. So we are fine. Now let's look at A2. Let's look at A2. So A2 appears in with X in A even and with X squared in A odd. And if we look at A4, it appears with X squared in A even and X4 in A odd. So how can we obtain those elements? So we can just use, okay, we can evaluate A even for X squared. So we replace X squared every time we see X. So we will obtain that A2 will be times X squared, A4 will be times X to the fourth, and so on. What about A odd? So A1 here appears without any as a constant term. Here is the linear term. Now A3 appears as with an X, so it's the linear term, and here is the cubic term. So we can do roughly the same for going. So if we do the same as we did for A even, we will have that A odd will be A cubed times X squared. So we will miss 1x here, 1x for A1. So we can just multiply the X in the front of A odd and we have done. Okay. So this is how we will combine AX even and AX odd. So now the conquest step. So we want to recursively compute A even and A odd. So we know how to evaluate them. So we will use basically the induction. So we want to evaluate A even with a set of Y's and A odd set of value Y's, where Y is in the subset of capital X squared, which basically is the set of X squared such that X is in capital X. Okay, so we will take all the points in the set of X and we will square them. Okay, so that we can evaluate correctly A even and A odd, and we will evaluate them. Okay, now, what is the complexity of this recursive function? So we have two elements here that play a role, which is the one is the length of the array of the polynomial, which is n. Okay, and the second one is the number of points that we have to evaluate, which is the cardinality of X. So this is the number of points that we have there, which originally, the first step, they are n, okay? Because we have n points, okay? So how can we, so now this, we will call twice the same function t for A even and A odd. A even and A odd as they have n over 2 the coefficients, so the polynomial is of degree n over 2, and we will evaluate in the size of X squared, which is n. And now the combined step. The combined step is 6 times n, because we need to concatenate them for all the points. So plus the cardinality, well, okay, of X. Okay. Now, if we draw the recursion tree, we will have that in the root, the total amount of time of the combined step is linear, so you O of n. And when we go into the two children, the recursion step, so t n over 2x, so here the size of n will be n over 2, but the size of x will be still n. So we will have n here and n here. So if we divide again the function, each time we recurse, we will spend n time. So at the end, we will have a bunch of n's. The height of this tree is log n. Okay. So the total amount of work that we do here is 2 to the log n, which is n. So this means, so you have n leaves, okay? Each of them spend all of n time to do the computation. So we still not have finished. Independent nodes, it is 2t and also not 2t. Okay. Well, this should be x squared because the number of points that you want to evaluate are the number of points in x squared. Okay. So now the size of x squared is the same of x. But we will see how to so what we want. So we are still not done. And the problem now is the size of x and the size of x squared. Okay. So in the size of x squared, we have a problem because it never decreases, it's still n. So what we want to do, we would like to find a set we want to find a set x such that the cardinality of x squared is equal to the cardinality of x divided by 2. And x squared has the same property of x unless the size of x squared is equal to 1, okay? So, okay, so I will write the title of this section later. Let me take some space, okay. Now, so what we want, so we will call a set of this property a collapsing set. So a set x is collapsing if the cardinality of x squared is equal to the cardinality of x divided by 2, and x squared is collapsing. Or the size of x is equal to 1. Okay, so how can we build such set? So we can take, so if the cardinality of x is 1, we can take a simple set, which is 1. Now, if the cardinality of x is equal to 2, well, the set of x, so what we can think is which are the two numbers, a and b, with a different from b, such that a squared is equal to b squared is equal to 1. Okay. So 1 to the power of 2 is 1, but also minus 1 to the power of 2 is 1. Takes x equal to 3. Again, so now we want 2 pairs of A and B such that they are different and A squared is either 1 or minus 1. So for 1, we have the same. Now, for minus 1, we want that A squared is equal to B squared is equal to minus 1. Which are the 2 elements which squared gives us minus 1? Okay, we can do the same. We can do the other direction. We want the square root of minus 1 is equal to plus minus A in this case, or A and B. So square root of minus 1 is I, the imaginary number. So here we have plus I and minus I. Okay. Make some space here. So you got the idea. So, and next, we have plus minus 1, plus minus I. So this part of the set is still the same. And now we want to compute the roots of I plus I and minus I. They are plus minus square root of 2 over 2 of 1 plus I and plus minus square root 2 over 2 of 1 minus I. Okay, so those are called the nth root of unity. Okay. Those are the nth root of unity. And how can we visualize them? Sorry. So those are x equal to 4. You have okay. No, sorry. No, I did it wrong. It's not 3 here, 4. But I need the power of 2. That they double all the time. Sorry. Thank you. Okay, so how can we visualize them? We can plot them in the imaginary and real plane. So here you have 1, and then the roots of 1 are plus and minus 1. Okay, and then the roots of minus 1 are plus I and minus I. Now the roots of plus I and minus I are those ones. Those points here, 1, 2, 3, and 4. This corresponds to square root of 2 over 2 minus a square root of 2 over 2. And here you have this is minus I square root of 2 over 2. And those are I square root of 2 over 2. And you can see that all those points are on the unit circle. Okay, this is the unit circle. This one here. So we can, so what we can see is that, okay, let's do it like this. We can write them in the vector notation. So we have a vector here, which has the length of 1, because this is the circle of radius 1, which form an angle that is theta here. And we can write this as a pair. So the coordinate on this plane can be wrote as a pair that is cosine of theta and sin of theta. Okay, because the component of the x-axis is the cosine of theta, and the component of the y-axis is the sin of theta. Okay, so those can be seen as cosine of theta plus I sin theta. So this is the notation A plus IB. Okay, this is the one that we used here above. Okay, and we have that this is equal to E to the I theta, and this is the Euler formula. Okay, so what does it mean? It means that each point in this circle can be written like this for theta. So now we want to choose n different angles. Okay, we want to choose those n angles equidistributed in this unit circle to get this root of unity. Okay, so we want to choose n equals spaced values of theta. So you can choose 0, then 1 over n tau, 2 over n tau, and n minus 1 over n tau, where tau is 2 pi. Okay, shorten the writing. Okay, we are running a little bit out of time. I will try to get it finished. Now, the thing is, now you can see that, okay, I will tell you this, that if n is equal to 2 to the k, so it's a power of 2. If n is a power of 2, then the and roots of unity is collapsing it's a collapsing set. Okay, how can you see that? Basically, the idea is that when you take a power of a point in the unit circle, when you take the square of a point in the unit circle, so what you get, you double the angle. So if this is the angle, you double the angle with respect to the x-axis. So if this is 45 degrees, when I take the power, it goes here, okay? If this guy here is 19 plus 45, 125 degrees. If I square it, it goes here, okay? So if I, for example, the simplest one, if I square -1, I double the angle, which is pi. I go to 2 pi. So the square of -1 is 1, okay? The square of 1 is itself because the angle is 0. You can see it using the formula, the Euler formula. So e to the I theta. If I square it, what I get is e to the I of 2 theta. I double the angle. And I can consider it 2 theta mod. Why? It means that I don't care how many circle I made around the origin, but I will consider it again. It's the angle within the x-axis. So if I take, for example, this point here and I square it, I will get this point here. But I will not consider it like 360 plus 180, but I just consider it 180, okay? Okay, so if you play a little bit, you will see that this claim is correct. So that this set for any that is a power of 2, it's a collapsing set. So every time we square it, we will get a set with half of the size of the original one. So, and this is enough for us to get n log n time algorithm. Why? Because now you will have that the size of x will be n at the beginning, but now here is n divided by 2, and here is n. But when we recurse, so the recursion tree will be n, then n over 2, and n over 2, and n over 4, n over 4, n over 4, and over 4. So at the end, we will have all ones. Okay. So in total, you can apply the master theorem. We get n log n. Okay, because the size of the set decreases by 2 all the time. So now we are ready for the fast Fourier transform. Okay. So the fast Fourier transform we said is divide and conquer. Algorithm. To compute the discrete Fourier transform. So how do we do that? So what we want to do, we want to given an array A of coefficients. We want to find an array of samples, okay, which is equal to the Vandermonde matrix times the array A. Now, what we need to do is we need to define the values of the matrix. Okay. Okay. So we need to define what is V of JK. And we set it as XJK, which will be A to the I JK tau divided by N. Okay. So we will do it like this. And basically, what does it mean? It means that we are dividing the angle according to the product of JK. So this is our vector that represent the points. Okay. Okay. And this gives us the claim of n log n time. So this was done by Cooley and in 1965, but it was already used by Gauss. So they rediscovered it in some way in the 1805. Okay. Now, okay, just 1 second. Yes, so here what we have is, sorry. Is that we choose xk as eik tau divided by n. Okay, and we said that n is a power of 2. Okay, so now in the last 5 minutes, I will try to tell you how to do a fast polynomial multiplication using the fast Fourier transform. So what we will do, so we have the 2 polynomial A of X and B of X. We take A star is the fast Fourier transform of the polynomial A. So A here is are the coefficients, and we got the samples, which are A star. Those are the coefficients. Those are the samples. Okay, we do the same for B. And now we can multiply them. And now the last part, we want to recover C. How we do that? We use the inverse fast Fourier transform of C star. So what is the inverse of the fast Fourier transform? Well, so basically what we are doing is we go to the coefficients, to the samples, coefficients to samples. And here we want to go to the samples, the coefficients. Okay, so this is quite easy. So the idea is we have to change only the values of the xk. So we just run the same algorithm. So the fast Fourier transform. The only thing that we do is we change the values, the points in which we evaluate the function, basically. Okay. So just 1 second. Oh, I lost my notes. Okay, yeah. So we have time. Yes. So basically the idea is that I make a claim. So what we want to do is we want to find that A is equal to V minus 1 times Y, okay? So this is what we want. So my claim, this is not here. My claim is that V minus 1 is equal to V complex and conjugate to CA star. What? Okay, so divided by n, where given we have that AIB complex and conjugate is equal to A minus IB. Okay, so this is the idea. So basically what we are doing, we are computing x prime k as A to the minus I k tau divided by n. So we just took the previous value of k, xk, and we put a minus 1 here, for example. Okay, put a minus 1 here. So we take the complement, the complement of the imaginary number, complex and conjugate. Okay. Okay. So this x prime gives me van der Waals matrix V prime. So what I will do is I will multiply V prime times A star, which are the samples, okay? And this will gives me n times A, okay? And then I will just divide it by n, and then I will obtain A, okay? So do you want me to prove this, or do you want me to prove this, or do you have questions? I can spend the time to clarify what I said so far. Also, we have a minute, so I guess it's very difficult. So the sketch of the proof is that you can prove that V times P complex and conjugate is equal to n times the identity matrix. Okay, so you can prove that. And this gives you the inverse fast Fourier transform. Okay, let's say that this concludes my the lecture. Okay, so we are done. And I don't know, but I guess Professor Deghi told me that probably this part will not be part of the exam. So maybe you will, what you will bring home will be the idea of the algorithm. But this part should not be part of the exam, I guess. Okay, maybe you can double check with him, but he told me that. And do you have any questions? So this is more or less, this is very similar to the lecture that Professor Demain gave, that Eric Demain gave. It's, which is also similar to what you can find in the CLRS book. It's the same. There is the whole chapter in the book, which is chapter 30, which is which it's devoted to the fast Fourier transform. Okay. I stop the recording now.